Okay, so we been talking about here in chapter 2, really sort of the idea of electrons and, as they sort of transition from one energy level to the next, um, sort of what happens in terms of that energy. And as we've been talking about, as an electron transitions, say from a higher energy level to a lower energy level, again, because of that idea of the sort of conservation of energy, the electron really has to sort of give off that energy to come back down from a higher state to a lower state. The result of that is basically the atom going to give off that energy in the form of a photon, as we talked about last time as well. If it does sort of fall in the visible part of the spectrum, the wavelength of that photon of light that comes off, then obviously we'll see a color. So, that kind of Roy G. Biv visible part of the electromagnetic spectrum. As we also talked about as well, these electrons, as they're transitioning, doesn't necessarily always mean that the transition will result in a wave that sort of comes off in that visible part of the spectrum. You could have a wave, obviously, that comes off in some other part of the spectrum, maybe the infrared spectrum, ultraviolet spectrum, and so forth. But, when we do get those sort of transitions that occur, that produces sort of a photon of light within that visible part of the spectrum. Again, that's sort of where we're able to see color. Excuse me. But we can figure out the sort of energy associated with that transition of those electrons from one energy level to the next using that equation that we did towards the end there. And that was, get something right with here. That was the one we saw that basically the change in the energy of the atom is minus 2.18 times 10 to the minus 18 joules. That again is Rydberg's constant. 1 over n squared final minus 1 over n squared initial. N is the principal quantum number. It really is sort of the energy level that we're talking about the electrons sort of transferring from. Remember that when we do calculate something like energy, it's important to keep the positive or negative sort of sign that you get with that value. Again, as we talked about last time, that really does indicate whether or not, in this sort of example here, is the atom sort of giving off energy as those electrons sort of transfer down, or is it absorbing energy? Typically, when we look at what we've been looking at, which is sort of the emission spectrum, that usually implies that those electrons are coming down in terms of energy, going to be given off that energy in that form of a photon. And for the atom, we typically would expect the energy to be more negative, as it's exothermic and releasing that energy as those electrons sort of transition down. Vice versa, if they're sort of in the absorption phase, like in the couple of labs that we did, either putting it into the Bunsen burner or the fire, absorbing the energy, or when you kind of click on the electron discharge tube there in electrical current, that would be more absorption. The atom would be gaining the energy, and it would be a positive value for energy. And again, that's sort of how those electrons gain enough energy, right, to kind of go upwards to higher energy levels. And again, as they come back down, they relax that energy. So important when we do those sort of energy calculations, either with this one or the other sort of one that we saw with energy here, that we do keep the positive or negative that we sort of calculate. Now, we have this one, which is H is Planck's constant, again, that being a constant number. So you always have that guy there. The frequency there being reciprocal seconds, and obviously equals hc over the wavelength, another sort of version of that equation coming from our speed of light, which is also, again, a constant value here. And this, as we saw, can tie into those equations as well. So this would also equal hc over the wavelength, and also equal h times the frequency. So by doing this sort of energy change when those electrons are transferring, we could also figure out the wavelength associated with that photon of light that's coming off as those electrons are transitioning, and also the frequency associated with it as well. We did a number of examples here, which was this example where we calculated all those things. So remember, again, the major couple issues, you want to make sure that you, obviously for all this stuff, make sure you use your exponent button. And then obviously as well, we want to keep the energy value positive or negative, but we do want to get rid of it because if we are going to continue on with a calculation, because we should always end up with a wavelength or frequency, both of these guys should be positive numbers. So again, you want to make sure if you're going to use that energy value that you do sort of get rid of the negative if it is negative. Also remember that depending on sort of the information that you have, there's a variety of sort of ways that you can kind of go through and calculate some of these things like the wavelength, the frequency, and those type of things, or the energy, depending on sort of, again, the information that you have. Any questions on any of that stuff there that we kind of talked about and did some more examples of during lab and the calculations on that? Okay. And again, a reminder that you are responsible to know the formulas, any type of constant values, like Planck's constant there, H and C, would be provided for you. Even Rydberg's constant, I think, will be provided for you. But you do need to know the formulas. They will not be, again, provided for you. All right, so since we did this guy here, so the other sort of thing that we were sort of in the middle of was this idea of Bohr's model of the atom, and whoops, come back. And a couple of things that we were talking about in terms of sort of Bohr's model is the idea that, you know, his model was this sort of planetary model where, you know, we have the nucleus, we have these orbits where electrons are found, and they're sort of traveling in these nice pretty circles and orbiting sort of the nucleus, again, sort of referred to sometimes as the planetary model of the atom. And what we're going to talk about today is sort of, we're going to be kind of transitioning away from Bohr's model of the atom, as we talked about last time. You know, it works really well for those lines that we see in hydrogen. And we talked about that sort of last time as well, the idea of sort of a continuous spectrum versus a line spectrum. Continuous spectrum, again, I think the example I used was like walking up a ramp. You technically could step anywhere along the way on a ramp as you kind of go up a hill. And that's what we see in a continuous spectrum. Pretty much all the wavelengths of light sort of come off at once. And that's different than sort of quantized energy, which is what we see with elements. Elements, because they have these quantized energy, which means, again, they have enough energy to be either at one energy level or the next, never kind of in between energy levels or anything like that. We end up seeing the more distinct line spectrum, as we looked at yesterday, and we talked about yesterday. They will emit these sort of specific lines at specific wavelengths because they either gained or lost enough energy to get to one energy level or the next. Again, that's more as like a staircase, like you're on this step or you're on the next step or you're on the next step. You again, typically if you're going up and down stairs, you don't find yourself stopping sort of halfway between a step because you probably will fall. So same idea here in sort of the quantized version of energy. You know, you're either here on this energy level or that energy level and so forth. And that's why, like we sort of did in the experiment yesterday, because elements sort of typically give off these line spectrums, every element sort of gives off a unique line of spectrum. So you could, as we sort of did yesterday in lab, sort of use what colors you see at what wavelength to determine what element you may be dealing with. So as we sort of move away from Bohr's model, some things about, you know, things like electrons and how they're moving, you know, sort of transition away from that planetary model of those electrons going around and around. Another very important sort of idea that we sort of talked about is this sort of dual nature of sort of light, if you will. The idea that particles can have wave-like functions and waves can have particle-like functions, sort of that dual nature of light. And de Broglie was the next sort of guy who actually didn't do actually any experiments really. He just sort of theoretically thought about this, that he proposed that particles could basically have that wave-like character. And he predicted that the wavelength of a particle is inversely proportional to its momentum. And because sort of particles are relatively small, the wave character of something like an electron, which is a particle, is significant. And this is what is sometimes referred to as the Broglie wavelength. And this is the wavelength is equal to h divided by the mass and divided by the velocity here. Now, h is Planck's constant, and there's actually, this is missing another second, so there should be a second actually there. But this is Planck's constant, which is our h, divided by the mass, that's in kilograms, and the velocity in meters per second. So the units are really important here. That's because Planck's constant is joules times seconds, right? So if we just kind of put our units in here, joules times seconds for h. Our mass needs to actually be in kilograms, and our velocity in meters per second. So you may be asking, why does the mass need to be in kilograms? The mass needs to be in kilograms for that relationship that we saw, I think, yesterday as well. A joule is a kilogram meter squared second squared. So remember, a joule is basically equal to a kilogram meter squared second squared, which is where that is coming from. That's basically a joule. And if we put those units in, we do need our mass to be in kilograms so that it will properly cancel out a meter here, and one of the meters will go there. 1 second here will take out 1 second there, and a second here will take out the other second there. And what you will be left with is meters, which is good because that is a wavelength. So the good news is h is 6.63 times 10 to the minus 34 joules times seconds. And if you do that conversion, the number doesn't change. It's still 6.63 times 10 to the minus 34 kilograms meter squared second squared times seconds. So they're the same. So the number really doesn't change here. So although the units technically do, this number doesn't change. So the key on using sort of de Broglie's wavelength is you got to make sure your mass is in kilograms and your velocity is in meter squared second squared, to make sure that everything does cancel out correctly. Any questions on that there? So again, it was interesting. He didn't actually do experiments, but later was found through experimentation that he was sort of correct in this idea of basically this sort of particles having these wave-like characteristics. Again, particles like electrons. So why don't you take a moment here and see what you come up with. An electron is traveling at 2.65 times 10 to the 6 meters per second. What is the de Broglie wavelength here in meters? What is that? 9.09 times 10 to the minus 28 grams is the mass of an electron, right? So take a couple of minutes here and see what you come up with. Okay, so let's take a look here. So we can calculate the de Broglie wavelength, which means we definitely want to use the formula we just saw. And again, a couple important things about this one. H is Planck's constant, so that would be our 6.63 times 10 to the minus 34 joules times seconds, divided by our mass. Again, when we're using this, it has to be in kilograms. I happen to give it to you in grams, so we do want to do a conversion. So we got 9.09 times 10 to the minus 28 grams. There's 1,000 grams in a kilogram. That will give us 9.09 times 10 to the minus 31 kilograms. So we got to make sure we do that conversion, especially using this one. Otherwise, we will end up with the incorrect answer. And our velocity was already in meters per second, which is perfect in this particular case. And again, basically, this is 6.63 times 10 to the minus 34 kilograms meters squared second squared. Again, all that is basically a joule. And again, time seconds divided by our 9.09 times 10 to the minus 31 kilograms, and our 2.65 times 10 to the 6 meters per second. In terms of units, kilograms now cancels. 1 second there, 2 seconds there, cancels both of those seconds. And one of the meters cancel, again, leaving us in meters, which is good because that is a unit of wavelength, which is what we're looking for. And if we do all that good stuff there, making sure we use our exponent button there, looks like we end up with something like 2.75 times 10 to the minus 10 meters. That's a very small wavelength. Again, a particle very small, like an electron here, having a relatively small wavelength. Any questions on that calculation there? So although technically we're changing the units on H, the good news is, like I said before, really the number doesn't change. It's still the same number that you normally use. But the key is really the bottom two. You got to make sure both of those guys are in the proper units. Again, mass very commonly given in grams, so you got to make sure it's in kilograms. And velocity could be given in a variety of units. Meters per second, miles per hour, kilometers per second, something like that. So, you got to make sure that those guys unit-wise are correct. Any questions on that there? So I think they agree with us pretty good. All right. All right, so as we've been talking about this idea of Bohr's model, whoops, come back. As I said, it doesn't really work very well as we sort of introduce more electrons sort of into the mix past hydrogen. So what we sort of done is we sort of are transitioning away from that model of the atom to more of a quantum mechanical model of the atom, where, we treat sort of particles like electrons, like they essentially have a lot of wave-like character. So what that means is we move away from this idea like we had in Bohr's model, where, we had this sort of planetary model where I know an electron's here and is traveling in a nice, pretty circular path around the nucleus, to more of really how electrons sort of travel, which is we don't really know how they travel. They travel in a fairly random sort of pattern about the nucleus. We know, they are traveling around the nucleus. They are traveling in that empty space around the nucleus, but how they're traveling, where they're located at any particular point along the way, we really don't have a lot of information on that. And one sort of important idea that leads us to that is what is sometimes referred to as the Heisenberg uncertainty principle. And basically what it says is that there is a sort of limitation to how precisely we can know both things, basically the position of an object or particle like an electron, and basically how it's moving in that particular case. So in fact, as we know more about one, we know less about something else. So as we know more about how a particle is traveling, we know less about sort of where it's located. And that's the idea behind Heisenberg's uncertainty principle. And that is actually the formula here. Basically, the delta X is the uncertainty in a particle's position, and the delta MV is sort of its uncertainty in its momentum, and that's Planck's constant over 4 pi. So sort of as you know more about its position, you know less about its momentum and how it's moving. And there's just sort of uncertainty aspect of it, sort of rooted in sort of the wave nature of particles and stuff like that. So this definitely moves us away from sort of the idea that we had with Bohr to going where we know it's going around in circles, the electrons, to, well, they really don't travel that way. They travel in this really random pattern, and we really don't know exactly how they're moving, their path at which they're moving. And as we'll talk about as we go through this sort of quantum mechanical model, we look at more sort of where we find electrons in the atom in terms of sort of probability. So like we could say, hey, there's a pretty high probability that we would find an electron in this particular part of the atom. Again, we don't really know, based on Heisenberg's uncertainty principle, we don't really know exactly where that electron may be, how it's moving, or where it is at any particular point in time. We just know that perhaps there's a pretty good probability of finding an electron in a particular location. So some more sort of quantum mechanical ideas about electrons and sort of how they're moving was done really by a guy named Schrodinger, and he did a lot of what I refer to as wave functions, and we're not going to get into it in great detail here. If you ever take physical chemistry, that you do get into it into very great detail. It's like calculus, derivatives, and all kinds of fun math sort of calculations that are involved. But the idea here is sort of with this wave function is this idea of, as I was just saying, that we sort of move away from this idea of, in Bohr's model, of knowing exactly where, we expect to find an electron, how it's traveling, to this sort of uncertainty idea of, I'm not really sure how it's moving the electron. I'm not sure at any given point where it's at. But as I was just mentioning, there is probably a fairly good probability that I could find an electron in a particular location within the atom. And as we would imagine, we think about our nucleus, which is positively charged, we think about our electrons, which are negatively charged. There's probably a fairly good probability that you would find an electron kind of floating around in that space near the nucleus, as one is negatively charged and one is positively charged. So they're going to have that opposite attraction. So what we end up kind of settling on in terms of this idea of sort of quantum mechanical model of the atom is these sort of probability maps, if you will. And these probability maps basically give us the idea of where there's a very high probability of finding an electron in an atom. And these probability maps are essentially moving us away from the idea of orbits to this idea of orbitals. And orbitals are really just as sort of probability maps, theoretical sort of probability maps within an atom of where you can find an electron or have a high probability to find an electron. And we usually refer to these as atomic orbitals. And you may be familiar with these atomic orbitals. These are the ones you use for electron configuration: s orbitals, p orbitals, d orbitals, f orbitals. And when we talk about these orbitals, there's a couple of important things. Electrons can be found in individual orbitals. And each individual orbital could hold a maximum of 2 electrons. And as we'll see in just a second, if you remember s orbitals, there's basically just one type of s orbital, which means it can max out in terms of 2 electrons. P orbitals, there's 3 different types of p orbitals. And that means if you filled up all 3 of those p orbitals, you would max out at 6 electrons. D orbitals, there's 5 different types of d orbitals, which means you can max out at 10 electrons. And f orbitals, there's 7 different types, which means you can max out at 14 electrons in that particular case. So let's take a look at sort of these orbitals here. Let me actually just let's see here. Just go ahead and we'll kind of skip ahead and come back here. Let's go here. So let's take a look at sort of these orbitals here for a bit, and just to remind everybody what they sort of look like and that kind of stuff and what's going on with them. So these are s orbitals, and s orbitals are basically just spheres. And this sort of, again, dark area here is sort of what is referred to as sort of a high probability of finding an electron. There's also these kind of areas which are known as nodes, and nodes basically goes back to sort of de Broglie and the idea of like a standing wave. If you think about like a guitar string, right? If you pluck a guitar string is basically attached to the guitar, which means it's like a standing wave. So you got this wave that's coming along, right? And there's areas where there's no amplitude, basically, right? Amplitude is basically the height of the part of the wave. So there's no amplitude, and those are nodes. And it basically, this wave is a standing wave. It can't really transmit too far away. It's sort of bound to the guitar. Same idea here where our sort of nucleus is, you know, the electrons are acting sort of as a wave, and they're sort of tied to the nucleus, but they are at some distance sort of moving around in a random sort of pattern. When we look at the s orbital, again, it's basically a sphere, and it does get bigger with each energy level. So like on the first energy level, n equals 1, you know, we have a 1s orbital, and that's what the 1 stands for there, is basically n is equal to 1. When you go to the second energy level, we also have an s orbital, but that's referred to as a 2s orbital, higher in energy, and the 2 again stands for the second energy level. Same thing here with the 3s, it stands for, again, the third energy level as to where you find that. Now, s orbitals, as you may be familiar with, s orbitals do basically start on the very first energy level. So on the very first energy level, n equals 1, that is where s orbitals begin. And remember that, as we talked about, n equals 1 is the ground state. It is the lowest in energy. It is the closest to the nucleus. And that is where basically s orbitals begin. They are found on every energy level after that. Now, p orbitals, there are 3 different types of p orbitals. This is our px, our py, and our pz orbital. And that basically just means that they're on different sort of axes in 3-dimensional space. They have basically different orientation. And, you know, there's a probability of where you would find sort of an electron. And again, you can kind of think of the nucleus sort of being in this area. And again, a high probability sort of finding those electrons, you know, sort of in this area in p orbitals, as the sort of nucleus is there in the center. Again, each of these guys could hold 2 electrons. That's where we get our 2, 4, and 6 electrons if we fill up this entire, what is referred to as a subshell or sublevel. A subshell or sublevel, it comprises of every orbital that's on, every same orbital that is on that particular energy level. With S's, we really don't talk about it as a subshell or sublevel because it's really just one orbital present. But here we have 3 different individual orbitals. All 3 of those together represent the p subshell, which can hold, again, our 6 total electrons in that particular case. Now, this is our d orbitals. And again, you can see we have 5 different d orbitals, our x squared, y squared, and all these kind of guys here. They basically look like pretty much a couple of p orbitals kind of put together except for this guy, kind of like a p orbital with a donut in the middle. But these again are probability maps, these areas of, you know, sort of darkened areas here, which really correspond to within here, these spots. Those are areas where, again, you would perhaps expect to find an electron, not really knowing exactly, you know, where it's at that point or how it got there. But again, this idea more of probability of where you find an electron rather than knowing for sure an electron is traveling around in a circular path. Then we obviously have our 7 different f orbitals. They kind of look like a couple of d orbitals together. And you can see again, each of these guys would hold obviously 2 electrons, and this would be referred to as the F subshell or sublevel, which again could hold a maximum of 14 electrons, 2 in each of these guys. Just like back here, this would obviously be the D subshell or sublevel. So obviously those are really important for electron configuration. And we're now going to really sort of talk about, you know, how do we sort of come up with this idea that there's like 7 f orbitals, there's, you know, 3 p orbitals, what energy levels they're on and stuff like that. And we're going to kind of talk about sort of, you know, how we kind of come up with our electron configuration that you might be familiar with. So let's go back to where we were here, which was here, I think. Okay, so again, those are our different atomic orbitals, or sp, d, and f. And again, what we refer to as a subshell or sublevel, again, is our orbitals on that energy level, all of the same ones. So as we were talking about a little bit before, here's again sort of what is referred to as a probability sort of map. And you can see, perhaps hopefully on your screen as well, you know, there's a change in this sort of blue color. Again, think of the nucleus is sort of in the middle, kind of where we see the darkest blue. Again, a much higher probability of finding an electron near there. Probability really starts to go down and gets lighter as we sort of fan out from the nucleus. And that's what we see here as the distance from the nucleus kind of goes. The probability of sort of finding an electron gets much, much, much smaller, as opposed to if we're really near the nucleus, we have a pretty high probability of finding an electron near there. Again, based on Heisenberg's uncertainty principle, not really sure how it's traveling, where exactly it's located at any particular point in time. Now, it's difficult to sort of define precisely the orbital size. The orbital, again, is this sort of wave function, which is sort of like a probability of finding things. We do picture an orbital as a sort of 3-dimensional electron density map, as we just saw there. And again, our hydrogen 1s orbital, the radius of it includes about 90% of the total electron probability. Basically, because it's a 1s orbital, it's a sphere, it's very close to the nucleus, it's on the lowest energy level. So again, very high probability of finding that electron in that area near the nucleus, for sure, in that 1s orbital. 1s, again, a reminder, when we do write something like electron configuration, like 1s1, 1s2, again, the first number that you see there is the principal quantum number. And again, that's basically the energy level. And in this case, it would be that n is equal to 1. The s is obviously the orbital where we have our electron basically hanging out in that particular case. So let's talk a little bit about these quantum numbers and sort of how we calculate the quantum numbers for electrons. So there really is 4 different types of quantum numbers. The first one that we've kind of been talking about and off and on here is the n, which is the principal quantum number. And it's basically the size and energy of the orbital. It's kind of like the energy level. N can have a value of 1 through 7. And as we talked about a couple of times already, n equals 1 is our ground state. It is the lowest in energy. It is the closest to the nucleus. And anything above that, kind of n equals 2 through 7, are what are referred to as excited states. And these are obviously further away from the nucleus and higher in energy. Now, the next quantum number is what is referred to as the angular momentum quantum number, and that is sometimes abbreviated as L. And that basically gives you the shape of the atomic orbitals, sometimes called the subshell, as we just talked about. It kind of tells you basically, are you dealing with a s orbital? Are you dealing with a p orbital? Are you dealing with a d orbital? Are you dealing with an f orbital? And L, we'll go down here. L can have values of 0 to n minus 1. So L can have values of basically 0 to n minus 1. And the next quantum number is what is referred to as the magnetic quantum number, or m sub L. And the m sub L basically tells you the orientation of those orbitals in three-dimensional space. It also kind of tells you how many orbitals there are in a particular subshell, but it technically gives you kind of the orientation in three-dimensional space. The m sub L can have values of minus L to 0 to plus L. And these are all sort of whole numbers as you go from there. And the last sort of quantum number, there's 4 quantum numbers. The 4th quantum number is what is referred to as the spin quantum number. And the spin quantum number is not there, apparently. Where did I go with that? No, I'll just put it here then. Is the m sub s, which is the spin quantum number. And it could have values of plus 1/2 or minus 1/2. And basically the spin quantum number has to deal with an individual orbital. So if we represent an individual orbital here with a line, when we put electrons into an orbital, they will have spins. They have their own spin. They're affected by a magnetic electrical field. The sort of electron pointing upwards, or the first one that goes in, has a spin which is referred to as plus 1/2. The electron that goes in kind of pointing downward in an orbital has a spin that is minus 1/2. So what does all this sort of tell us? Well, it tells us sort of how many orbitals we have, where these orbitals are located, what energy level are these sort of 4 quantum numbers. So let's take a look at this here. Perfect. Oops. Find that page. So let's take a look first off at just what's happening on our n equals 1. So n equals 1 is the lowest in energy level. It is the ground state. And we want to know sort of what is available there. So this is sort of our energy level. Now with n equals 1, L could have values of 0 to n minus 1. So what that means is the acceptable value for L would be 0 to n minus 1. N is 1, 1 minus 1 is 0, which means the only acceptable value you could have for L on the first energy level is 0. What does that mean? Well, that means that the type of orbital that we're dealing with in this particular case is an s orbital. So when you have an L value that's equal to 0, that represents our s orbital. And m sub L means that it could go from minus L to 0 to plus L. Since L is equal to 0, 0 to 0 to 0, the only value you could have is basically 0. And again, that's sort of the orientation in three-dimensional space, but it also tells you how many orbitals you have. Also the 3D sort of space and orientation. There's only one number there, which means you could have basically one s orbital. And m sub s can be either plus or minus 1/2. So what does all these sort of things mean? These things mean that based on the 4 quantum numbers, on the very first energy level within an atom, the only orbital that would be there would be an s orbital, and it would be referred to as a 1s orbital. There's only one s orbital, which is why we have just one line. And within that one orbital, we could put an electron going upwards, and we could put an electron going downward. Any questions on that there? So let's see what happens when we look at n is equal to 2. This is now the second energy level. If n is equal to 2, we can have an L value that is equal to 0 and 1. Again, n minus 1 is 2 minus 1 is 1. 0 and 1 is where we get those numbers. So what does this mean? Well, this means that we have on this second energy level also an s orbital. But now we have another type of orbital that's there, which is represented by the quantum number 1 for the L. And that is going to be our p orbital that's represented there. When we do m sub L, we could do m sub L for each of these L values. So for our L value of 0, our m sub L would be 0 like we had before, which means we have on the second energy level just one s orbital. When we do our m sub L value for 1, it goes from minus L to plus L. This would be minus 1, 0, and plus 1. These again represent the 3D orientation of these orbitals in three-dimensional space. It also tells you if you just count up the numbers here, that's 1 number, 2 numbers, and 3 numbers, that is how many orbitals we have. 3p orbitals are present. And that means that on the second energy level, we have 3p orbitals that are present. This number here, minus 1, 0, plus 1, represents our px, py, and pz orbital that we are talking about. And for each of these individual orbitals, they both could have a plus or minus 1/2, which means we can put electrons heading in opposite directions into each of these guys and fill them up. Any questions on that there? Okay, so let's talk about then if we kind of went to the n equals 3 level, what happens at the n equals 3 level. So I'm going to let you take a moment or two and try to decide that. You need to decide what happens on the n equals 3 level. You know, what is our possible L values that we could have? And what is our possible m sub L values and m sub S? So take a moment and see what you come up with, and then we'll go through it and make sure everybody understands what all those numbers represent. Well, we're at the third energy level, basically. So really what we're going to try to determine is what are available there, what is possibly can be there in terms of orbitals and stuff like that. So with n equals 3, that means that we can have an L value that goes from 0 to 1 to 2 in this case. Again, L going from 0 to n minus 1. In this case, n is 3, so 3 minus 1 is 2, which means we can max out here basically at number 2 for our angular momentum number there. As we saw previously, a L value of 0 represents an s orbital. An L value of 1, as we just saw, represents p orbitals. And as you might be able to guess here, an L value of 2 would represent a d orbital. So for each of the L values, you can have an M sub L value. So for L that's equal to 0, as we saw earlier, the only acceptable value for M sub L would also be 0. Again, M sub L goes from minus L to 0 to plus L. And again, what that basically tells us what we saw before. We could basically have an s orbital on the third energy level. We basically have just one s orbital on the third energy level. And within that s orbital, we can have an electron that is either pointing upwards or downwards in terms of its spin. For our L value of 1, just as we saw a second ago, we can have an M sub L value that goes from -1 to 0 to +1. This basically tells us that there are p orbitals on the third energy level. There is 1, 2, 3 p orbitals on the third energy level. Again, this representing our px orbital, this number representing our py orbital, and this guy representing our pz orbital. And within each of those orbitals, we can put an electron going upwards or downwards in each of those individual sort of orbitals. Now, with our L that is equal to 2 in this case, we could have an M sub L value that is -2, -1, 0, +1, and +2. And if you think about our d orbitals, that is 1 orbital, 2 orbital, 3 orbitals, 4 orbitals, and 5 orbitals. So this is why we say that there are 5 different d orbitals represented by that x squared, y squared, x squared, all those guys that we saw previously, which is each of these numbers represent. Now you can, for each of those individual orbitals, basically put 2 electrons in, one going upwards, one going downwards. First off, any questions on any of those sort of numbers? So if we were building our sort of energy level diagram here with our orbitals, what we saw previously, again, on the first energy level, basically just have a 1s orbital. On the second energy level, a 2s orbital, and that is where we first start to see our p orbitals occur. On the third energy level, again, based on this, there is an s orbital. There are 3 p orbitals represented by this guy, and this is where we first start to see our d orbitals basically appear, represented by these quantum numbers here. Any questions on that there? Now, if we did our, say, fourth energy level, our acceptable L values would go from so the MS, we'll actually see in just a second how to apply sort of these quantum numbers to sort of the electrons in the atom when we do electron configuration. But basically the MS as either -1/2 or +1/2 is basically just a notation of how the electron is sort of placed within the individual orbital. We'll talk about in just a second why they are not sort of going in maybe both +1/2 or both -1/2, but they're sort of +1/2 and -1/2 sort of different sort of spins, and why they can't be the same in just a second. But so hold on to your question, I think, and I think we'll get hopefully to that answer in just a second here. But if we look at n equals 4, L can have values of 0, 1, 2, and 3. Again, L going to n -1, so 4 - 1 is 3. So as we saw previously, that is obviously our s orbital. That's going to represent our p orbital. that represents our d orbital, and you could probably imagine that R3 represents our f orbitals. Now we could go through each of these just like we did pretty much on this previous page. We could go through our L equals 0, and we would get all the same numbers. Our L is equal to 1, we'll get all the same numbers. Our L is equal to 2, we'll get all the same numbers that we had here. So if we add in our L is equal to 3 in this case, which is what we get on the 4th energy level here, we can again do our M sub L here, which would be -3, -2, -1, 0, +1, +2, +3. And basically, remember, this is sort of the orientation in three-dimensional space. But if we, as we talked about, also how many orbitals we would expect. So our 3 here, which is representing our f orbitals, would have 1, 2, 3, 4, 5, 6, and 7 different f orbitals. Each of them can have an electron either going kind of upwards or downwards in each of those individual orbitals. So if we add our n equals 4 here to our sort of chart, we would have obviously a 4s orbital, we would have our 4p orbital, we would have, let's draw smaller so I don't run out of too much room, 4d orbital, and on the 4th energy level, 1, 2, 3, 4, 5, 6, and 7, that is where we would again first start to see our f orbitals basically take shape. So this is the basis, sort of the quantum numbers and this sort of quantum mechanical theory and probabilities here of where we find these electrons. This is really where, you know, it comes from when they tell you originally, probably last semester, hey, there's, you know, 1s orbital, there's 3p orbitals, there's, you know, 7 f orbitals, and why it starts on this energy level versus the next. And it's based off of these sort of quantum numbers as to why we do this. Now, when we look at this, a couple of terminologies, which is important, and we touched upon some of this, but when we talk about a level or a shell, we are talking about everybody that is present. So if I ask, you know, how many electrons to max out the n equals 2 shell or level, the answer would be, when we talk about the n equals 2 shell or level, we are talking about everything that is contained on the 2nd energy level. And again, because each individual orbital can hold 2 electrons, technically 1, 2, 3, 4, 5, 6, 7, and 8 electrons would max out that n equals 2 level. If I ask how many electrons to max out a 3D subshell or sublevel, the answer would be 3D, which would be over here. A subshell or sublevel means that we are taking the entire orbitals within that, which would be all these guys. So if we were doing this guy, the answer would be, if we filled all that up, 2, 4, 6, 8, and 10 electrons in that particular case. So shell or level means every single orbital that you find on that entire energy level. Subshell or sublevel is referring to a set of, say, d orbitals, a set of p orbitals, an s orbital, I guess, in a sense, a set of f orbitals. You know, all those guys together would be a subshell or sublevel in that particular case. If I want to know how many electrons in a 4D orbital, take a second. How many electrons in a 4D orbital? The answer to that is 2 electrons. So again, when we're talking about a 4D orbital or any individual orbital, kind of talking about each individual line. Any of these individual lines could only hold a maximum of 2 electrons. But if we're talking about how many electrons can the 4D subshell hold, that is a grand total of 2, 4, 6, 8, 10 electrons if we take all those guys together. So that's, got to be careful on some of the terminology that we sometimes see. Any questions on that there? Now you may be wondering, okay, well, what happens like, since n could go to, for example, 7, what happens sort of after we get to the ones we're familiar with, the S, the P's, the D's, the F's. But before we do that, before we sort of move off of this page here, there is sort of a quick way that you could calculate how many electrons you can sort of put into an atom. And that is by taking 2 to n squared. So this was a quick way that you could calculate the maximum number of electrons in a level or shell. So for example, we did 2 a second ago. What you would do is 2 squared is 4, 4 times 2 is 8, which is how many electrons. If we were doing our third energy level, 3 squared is 9, 9 times 2 is 18 electrons. And that's what we could put here, 2, 4, 6, 8, 10, 12, 14, 16, and 18. So this is a quick way that you could kind of calculate the maximum number of electrons that you would put on a shell or level without having to sort of draw them all out and stuff like that. Questions on that there?
I have a question, Professor.
Yeah.
How did you get 2 electrons for the 4D orbital again? Because I was thinking it was going to be 10, but is it because 10 would be the subshell, or?
That's exactly right. Yeah. So sometimes I won't say it's a trick question, but sometimes it's very much asked sometimes. But whenever you're asked sort of how many maximum electrons you put in any orbital, S orbital, P orbital, D orbital, the answer is really 2.
Okay.
But if they ask kind of like what you just said there, how many electrons could you put in a 4D subshell? That 4D subshell would basically comprise of all 5 of those guys. And then you could fill all 5 of those guys up with a maximum of 10 electrons. But when we're talking about an individual orbital, we're really just talking about kind of one line at a time. And one line at a time, you can only put 2 electrons in.
So then how many electrons in a 3D orbital? It would be 2 electrons?
It would be, yes.
Okay, thank you.
Other questions on that? Yeah, so just like you just said there as well, again, if you were asked, how many electrons could you put in a 3p orbital, the answer would be 2. If you were asked how many electrons could you put in the 3p subshell or sublevel, it would be 6, because you could put 2 in each of the 3 of them, which would give you 6. Other questions on that? So as I was just mentioning as well, what maybe happens, if we kind of go above 4, right? Obviously, we could go up to 7 for n. So let's take a look at, say, 5. If n equals 5, we could have L values of 0, 1, 2, 3, and 4. You may be going, all right, well, I know that's now an S. I know that represents a P orbitals. I know that represents D orbitals. I know that represents F orbitals, but they never mention, what comes after that. So what technically comes after that is they got really creative. They just went in alphabetical order after that. So technically that would be G, and you would just go alphabetical orders, if you had 5 or 6 in terms of L and stuff like that. Typically speaking, normal electron configuration, we pretty much max out here. We never get into sort of G's or anything above that in sort of normal chemistry. But that's technically sort of how you would classify it, would be as sort of just continuing on in alphabetical order. So whatever letter comes after F, and then after that, you would continue on that way. And you would do the same thing, M sub L, in the case of L is equal to 4 could go -4, -3, -2, -1, 0, +1, +2, +3, +4, which means technically if you got up that high, it would have 1, 2, 3, 4, 5, 6, 7, 8, 9 different orbitals there, if I counted correctly, hopefully, along the way. So it just kind of goes alphabetical after F. In most cases, we never really get there in terms of electron configuration or writing electron configuration. But you may come across, obviously, a question where like, hey, n equals 7, what are the possible sort of L values and stuff like that? Questions on that? All right, let's see here. All right, so I think we sort of covered this guy here in our little talk there, but again, for n equals 3, determine the allowed subshells, the different L values, and give the designation. So obviously, if n is equal to 3, we could have, like we saw earlier, our L values running from 0 to 1 to 2. And again, basically what that would represent is an s orbital, p orbital, and a d orbital. And specifically because we're on the third energy level, they would represent the specific 3s orbital, 3p orbitals, and 3d orbitals. Remember, sort of when you write those things like an electron configuration, that first number is the principal quantum number. And I think we probably hit this guy as well along the way here. For an L value of 2, determine the M sub L. And again, remember that M sub L runs from -L to 0 to +L. And that means that we would run from -2. Again, whole numbers here, -1, 0, +1, and +2. This representing our 5d orbitals, and they're really their orientation in three-dimensional space. All right, so let's talk a little bit about, now that we have sort of an idea about quantum numbers, let's talk a little bit about electron configuration and really how the two sort of tie together here. And we just kind of went through these slides here earlier. We jumped ahead. Again, this is basically an L value of 1 representing, I'm sorry, an L value of 0. Let me get that right. An L value of 0 and an M sub L value of 0 here for our s orbitals. Again, probability in those kind of darker blue areas of where we would expect to find an electron. These again are our p values, which again starts at that second energy level, n equals 2, where we have an L value, actually this guy is 1, and an M sub L value of -1, 0, and +1 coming across there. And then obviously our d orbitals, where we start on our third energy level, and this is our L value of 2. And again, our M sub L value running from -2 to -1 to 0 to +1 and +2, again representing our 1, 2, 3, 4, and 5 d orbitals that we have. And obviously our F here, that starts on our fourth energy level, where we do see our L value getting up to a value of 3. And again, our M sub L running from -3 to +3, basically, if I knew how to count there, -1, 0, +1, +2, and +3. Rolling that way, again, representing obviously our 7 F orbitals. And like I said before, when we get electron configuration, that essentially is sort of where we max out in terms of it. So the question about sort of the spin, and let's just sort of talk about the spin here and what the plus and minus 1/2 sort of represents. Well, the electron spin represents the spin of the electron within the orbital. And something known as Paulie's exclusion rule basically states that no two electrons that basically are kind of sharing an orbital can have the same 4 quantum numbers. And so how do we get around that? Well, it is really with the spin quantum number. So let's just take, for example, hydrogen, which has, actually, let's take helium here first. Helium has basically 2 electrons, right? And they're both going to be in the same orbital. Now, if we take helium's, and by the way, it is 1s2, right? If we put this electron in here first, and we wanted to basically give the 4 quantum numbers for that electron, the first electron will always sort of go into the orbital pointing upwards. And if we were to give the quantum numbers for that first electron, n would equal 1 because it's on the first energy level. L would equal 0 because it's a s orbital that's sitting in. M sub L would equal 0 because it's sitting there basically in the only orbital that's available. And the M sub S would equal plus 1/2 in this case. Not plus or minus 1/2. It would actually equal plus 1/2 for the spin quantum number as it's pointing upwards, which gets the plus 1/2. So that would technically be the 4 quantum numbers for that electron hanging out there in that 1s orbital. Now, if I decided to put my next electron in there heading in the same direction, my electron now would have, in this case, a value of n is equal to 1, L is equal to 0 because it's in the s orbital, M sub L would equal 0, and my M sub S here would be plus 1/2. Again, also pointing upwards. The problem with this is this electron here and this electron here now has the exact same 4 quantum numbers, which is a violation of Paulie's exclusion rule. So we cannot have that occurring. We cannot put the electron in the same sort of orientation. So how do we get around that? Well, we get around that by basically putting our electrons in opposite directions. And what that means is this first electron will still have these 4 quantum numbers. The second electron now will have a quantum number that is n is equal to 1, again on the first energy level. L is equal to 0 because it's an s orbital. M sub L is also equal to 0. And now the spin on this guy is minus 1/2. Again, not plus 1/2, but minus 1/2 because it is heading downwards. Now, when we look at these 2 electrons that are sitting in the same orbital, they now have actually not the same 4 numbers. The only difference is actually the spin part of it. One is spinning upwards notation, one is spinning downwards notation. This is what is referred to as paired spin. And by that simple sort of difference that the electron is kind of going spinning upwards, the other one's spinning downwards, it gives each of those electrons that are sharing the same orbital 4 different quantum numbers. They don't share the same 4 quantum numbers, and that does not violate Paulie's exclusion rule. And that is why we have for an orbital electrons basically going in the paired situation, opposite spins. They essentially kind of cancel each other out in that particular case. Question on that there. And this is also why we couldn't put both of them in heading downward. If we put both of them in heading downward here in that 1s orbital, our n would equal 1, our L would equal 0, our M sub L would equal 0, and our M sub S would equal minus 1/2. And if we did it for our other electron, it would also hit exactly the same 4 quantum numbers, which again is also a violation of Paulie's exclusion rule. So this is why when we sort of denote it or draw it or talk about electrons within the same orbital, because of Paulie's exclusion rule, which states that they cannot have the same 4 quantum numbers, we always put them going in opposite directions. The electron always goes in upwards first. So when you put an electron in an orbital, up first, down second. So plus 1/2 in terms of the spin first, and minus 1/2 in terms of the spin for our second one. Question on that there. You could also maybe see that you could get very specific in terms of the quantum numbers for specific sort of electrons that you are talking about. Any questions on that there?
Can I ask a question?
Yeah.
So what if you had n equals 2? What would it be -3/2 and +3/2, or is that correct?
Are you talking about the spin?
Yeah.
Yeah, no, the spin will always be, no matter what energy level it's on, will always be either +1/2 or -1/2.
Oh, okay. Sounds good.
The one, if you're asking, is the one sort of is the one over here over 2 because of the energy level. It's not. It's actually just 1/2. So for the spin guy, it will always be 1/2, and it will always be +1/2 or -1/2, depending on sort of which particular electron you're talking about. So usually, always the first electron within an orbital will basically have that +1/2 notation, and the second electron that goes into that individual orbital will have the -1/2 notation for the spin quantum number.
No matter what, n equals 2, n equals 3,
Yeah.
always half.
Yeah, because this is more that those numbers are more referring to the individual sort of electron and its individual spin within an individual orbital. The other sort of quantum numbers, kind of the N, the L, and the M sub L, are speaking more about kind of the overall orbitals themselves and sort of where they're at. This one's more specifically talking about the electrons within a specific orbital, sort of how they're spinning and their orientation. Other questions on that? Okay. So atoms with more than one electron, we do see sort of a correlation problem in terms of the electrons. And again, sort of electrons are negatively charged, and they're obviously going to be near other electrons that are negatively charged. So we do get this sort of separation that occurs when we get more than one electron within an atom, because of the fact of, well, we basically have negative guys near negative guys. And as we've talked about, they really don't like to be sort of in that situation, right? They want to get away from each other. Clearly within an atom, they can't get any far away from each other, but they do sort of space each other out. And what ends up happening is we get this sort of difference in terms of the energy levels of the different orbitals that we see. And what I mean by that is if we look at what is sometimes referred to as the penetration sort of effect, because of all these sort of negative electrons hanging out in these orbitals, especially when we get into lots of electrons within an atom, definitely past hydrogen, obviously more than one electron, we get that effect of, we got a lot of kind of negative things near negative things. So much like in chemistry, what things try to do when they get those sort of like charges near each other is they try to spread out as best they can. Sometimes they could get pretty far away from each other. Other times they really can't get far away from each other, but they try to get kind of far away or far enough away from each other that they are sort of comfortable with it, if you will, or it's the best that they can do. And what that means is when we think about, for example, hydrogen and just one electron that's happening, if we were to look at the individual sort of orbitals that are there, say on the n equals 1, n equals 2, n equals 3 sort of level, we obviously have our 1s orbital. We then would have our 2s and our 2p orbital and our 3s, our 3p, our 3d orbital. And again, if this is sort of energy, everybody that's sort of on the second energy level, all the orbitals would be perfectly equal in each other in terms of energy. Next would be on the third energy level, all the orbitals are basically equal to each other in terms of their energy and where they're at. When electrons do go into the atom, what we typically see is the electrons always want to go in lowest energy first, and then to the highest energy, next highest, next highest, next highest in energy. I guess a better way to say it, lowest energy, next lowest, next lowest, and next lowest. So electrons really go into the atom kind of like how you walk up a stair. You start at the bottom step and you go next step, next step, next step until you get to the top, right? You don't just go and jump to the top and come back down or anything like that. So electrons basically fill into the atom lowest energy to highest energy. And what ends up happening when we start introducing multiple electrons within an atom is these orbitals here, there's actually kind of a shift that occurs in them. And the shift that occurs in them is really important in terms of how electrons basically go into the atom. What ends up happening when we get like multiple electrons happening is we do get like our 1s is the lowest in energy. Then actually we get our 2s orbital is lowest in energy. And then the 2p orbital is the next lowest in energy. And then our 3s, then our 3p, and so forth. So we actually get this sort of separation in terms of these orbitals, in terms of their energy. And what that means is the first thing that would happen is electrons would go and fill up the 1s. And then if we had more electrons, it would fill up the 2s. And if we had more electrons, it would then go to our 2p. And then once that's filled, go to our 3s and so forth. So because there's this sort of change in the energy of these orbitals, it does affect how the electrons basically fill the atom when they go in. And there's sort of a different order that sort of occurs, based on the filling of those orbitals and the differences that occur in the energy. So here we see sort of the difference between a 2s orbital and 2p orbital in terms of their distance from the nucleus. And again, we start to see some of our 3s orbital come out a little bit further from the nucleus. Again, these guys sort of acting as wave type functions, and our distances from our 3s, 3p, and 3d. So there's some difference in terms of the probability and where they locate. And basically what all this basically results in is the order at which we kind of put electrons into the atom and how we write basically electron configuration. So this is something that you probably have seen before. There is an order, and you could actually recreate the order pretty easily on your paper by going 1s, 2s, 3s, 4s, 5s, 6s, and 7s. Then going 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, 4f, and 5f. So this is something that you could recreate really easily. And if you remember from our conversation we just had, on the very first energy level, we only have s orbitals, right? Then when we get to the second energy level, which is what that 2 represents, that's where our p's start. Our third energy level, that's where our d's start. And our fourth energy level is where our f start. So if you just kind of do that and then go downward towards 7, you could recreate this. And this is basically the order at which electrons will fill an atom as they're coming through there. And what happens with this is you always start right here. So you always start up on top, and you basically do this sort of zigzag move. And this will give you the correct order at which electrons are basically put into the atom. Based on how those orbitals start to shift in terms of the energy. And the major difference where people kind of mess up is if we kind of follow this through, what we see is one S, we would go 1s, we then would zigzag back to 2s, we would zigzag back to 2p, 3s, which makes sense. We would zig back to 3p. And what confuses people is after the 3p, it is actually the 4s orbitals that are lower in energy than the 3d. So the 4s orbitals would get the electrons first, then you would come back to the 3d. And that same pattern follows. You go to the 5s and then zigzag back to the 4d. So there's that pattern when these orbitals start to shift in terms of energy because of the electrons that are present. We start to see that the s orbitals actually end up being lower in energy than the d orbitals, and they actually will get the electrons first. So this little chart here, along with understanding how many electrons you could put into an atom, will essentially give you the ability to write any type of electron configuration you would have to do. Any questions on that so far? Okay, so I think what we're going to do is we'll